Morning.
Okay, welcome everybody to this session in our complex analysis workshop. Rob is a recent addition to our program, but by now I believe everyone has met him. So Rob, it's over to you. We'd like to hear about your special functions.
Okay, thank you very much, Andre, and thank you very much for the invitation to come here. This is only my second visit to Cambridge. The first was, I think, 23 years ago. Anyway, been too long. So today I'm going to talk about special functions. Special functions is one of those topics which everybody has an opinion about, and in some sense the subject is too beautiful for anyone to be able to ruin it. So no matter how bad a talk I give today, you will get something out of it, and no matter what I manage to do. I hope that you'll enjoy some of the things that we found out of it, these special functions. But I should preface this with an anecdote. When I was a master's student at the University of Waterloo in 1980 or 1981, I overheard two of my professors talking about special functions. And one of them expressed the opinion that special functions are dead now, aren't they? That is absolutely not true. Even in numerical analysis, special functions have very large roles to play. I'm not going to talk about applications at all. This is I think I'll mention one at the end. This is really going to be a talk about a very old subject. So I hope you enjoy it. So the backstory of this particular paper, this particular talk, is that when John Borrowing was visiting me in 2016, I suggested to him that we were to do a similar paper to what he had done with pi. He and Scott Chapman wrote a lovely paper called I Prefer Pi. And they reviewed all of this is palindrome, they reviewed all the papers on pi in the American Mathematical Monthly. And it's a lovely paper, I highly recommend doing that. So I thought, well, why don't you and I do that about the gamma function? And John went, yes, excellent idea. So for 3 months, we talked every day about the gamma function and about papers in the American Mathematical Monthly. And it turns out that there's more than 50 papers on the gamma function since its founding in 1894. The American Mathematical Monthly is a very interesting journal. Almost everybody knows it, but most people might not be aware that it in fact is the highest impact mathematics journal in the world, according to JSTOR. It's always in the top 50, sometimes in the top 20, beating out chemistry and other kinds of journals. So it's absolutely remarkable. It has a rejection rate of more than 90%. So if you get rejected for the monthly, don't worry, it's okay. I have many rejections for the monthly as well, so it's all right. Anyway, John and I surveyed the papers in the monthly on that, and probably the best one. And here, if you take nothing else away from this talk, take the paper by Philip Davis, which won the Chauvenet Prize. It was published in 1959, the year I was born. And it's called Leonard Euler's integral. So note that down carefully, and that is well worth your time to read. It's absolutely a brilliant paper. There's a paper by Manju Bhargava, who won the Fields Medal in 2014, which is also very interesting to read. I'll move around a little bit more right now. And there's lots of other stuff. So we identified some gaps and surprises, which I wasn't expecting. I was just expecting a survey in Rome. But one purpose of the survey is just to see what's not there. So I'm going to switch to chalk here, and I'm deliberately bringing up both words because there's secrets underneath them. So how many of you, well, let's not take it up that way. So how many of you in the audience have written a book on the gamma function? It's a non-trivial chance that somebody, how many of you have written code for the gamma function to evaluate the gamma function? Yay? That's 1, 2, 2. There we go. How many of you have written a paper on something in the gamma function itself? Okay, there we go. How many of you have given a lecture to anybody, students, on the gamma function, a whole hour? Not quite a whole hour, just half an hour. Okay, arts. How many of you have heard a lecture? Yeah, well, that's most of it. Yeah, there we go. And have you read something? Just read something? Yeah, everybody's read something. Now, here's a hard question to answer in this audience. How many of you have never heard of the gamma function before today? Nobody's willing to admit it. I have given a talk where somebody was willing to admit it, and that was incredibly brave to stand up and say they hadn't heard about the gamma function. But just because we have all heard about the gamma function doesn't mean that everybody has. So, okay, all right, but everybody in the room has heard about the gamma function. All right, the test. Now comes the test. What do you recall? Give me some facts, any facts about the gamma function.
There you go.
There we go, the recurrence relation.
Let's make it X. So there you go.
I'm going to cap this at 5 in this audience. I'm going to quit when I hit 5. Another fact?
Stirling's formula. I want to hear it with the fine.
Sorry.
Stirling's formula.
Stirling's formula. Can you remember it?
Root 2 pi n to the n e to the minus n.
Well,
This is this for the half, yeah.
You know what the next term is?
12 somewhat.
12. People remember the 12. Do you remember the next term?
144 or 288.
280. Oh my God.
I wasn't laughing, but I said I've used it.
What power? Square?
That's squared. Oh,
The square. That's important. Wow. Okay, this is the only time. Another fact.
Gamma z times gamma 1 minus z is whatever, pi to sine x L.
Excellent.
That's right, just came with a half. Root pi.
So the reflection formula.
There's no differential equation.
Yay! That's not on the secret thing on the back. So gamma is what's called totally transcendental. So it does not solve any differential equation with that's polynomial in x and y. It's just there is none.
Double up roots. What about its roots?
Double up the poles, double and.
The double. Okay, that one I don't know. So gamma of 2z is some complicated formula.
Gamma z, gamma z minus 1/2, we want to see
Okay, this is the Legendre's duplication formula. Well done. It's actually, I have it in the paper, but it's not on the list. So, okay, that was fabulous. Here's a few more. I was kind of expecting this one, but who cares? We have the recurrence relation. We have Stirling's formula. That's actually enough. You can deduce everything that you need from there. I prefer the reflection formula in this way: minus z factorial times z factorial is pi z over sine pi z. It just looks nicer than gamma of 1 minus z times gamma of z. It's the same formula. This doesn't scratch the surface of gamma function formulas. I picked up a book from 1960 by Kratz and somebody, and there was a new version, well, a new version to me, of the reflection formula. Prim's formula I'd seen before, but it's not included in our paper. This formula due to Euler was new to me when I first read Philip Davis's. So this integral is actually the same as this integral. You just do change variables, get from one to the other. But boy, it looks strange. Here's Euler's first definition, and lots of people don't like this because it defines z factorial in terms of factorial, but it's okay because this is an integer factorial, which has a separate definition. Now, I put quotes around Stirling. That formula is not due to Stirling. It's due to De Moivre. And we will see something a little bit later. There's a difference between the logarithmic formula, where we only have 1 over z cubed, so we're missing the even terms, and the exponentiated version where we have the z squared. And you might think that this is advantageous, but one of Andre's colleagues had a little paper which said, actually, it doesn't help as much as you think you want. So I'm sorry, I've forgotten where that was, but I can find it. Okay, let's go back to the computer stuff. Moral of the story about using chalk and wearing dark clothes is wash your hands. But mixing with computers, well, do that. I'm just going to have to cope with chalk on my jeans.
tissue.
It's okay. It's okay. We're good. Some facts. I will mention this crazy shift by one. Why do we have two notations for the same function? And it turns out it was not Legendre's fault. It was Euler's fault. Euler used both, and we're now stuck with it. We have a minor but continual nuisance. And it's to add one, we just have to get used to it. Okay. Let me see if I can. So I told Andre that I have about 4 hours for everything. So I'm going to give you some choice about what we're going to do. I do want to talk a little bit about, well, I certainly want to talk about Stirling's original formula. I want to definitely talk about the functional inverse. But whether I talk about the series for reciprocal gamma, that's 1 over gamma z, and the reversion, or if I talk about the branch point versions, or Riemann surfaces, is kind of up to you. So I'll begin with section 3, and you can think about other things, and you can vote some of this stuff off the island. Don't throw tomatoes, Arthur, but we can. So let's just do some facts in here. We've gone over a lot of these things, but here's a graph of the gamma function and its derivative. It's logarithmic derivative. Psi is the derivative of log gamma, so gamma prime over gamma. And you see that gamma the real gamma increases monotonically after about 1.46 and has poles at all the at 0 and all the negative integers. Well, that's fine. And the formula prim actually gives us the residues at all those poles. So we actually know quite a lot about the poles of this function. Yeah, good. I'm going to skip over there, and I'm going to come to something that should look familiar from the web page of the program. We actually have a phase diagram of the gamma function is up in the upper left corner. This is from this lovely book of Uyghur, which we have the copy on the table down there. So we're looking here at the phases, and we can see, well, actually, until I show you the color map, you're not completely sure that those are poles. But if we look at the color map here, we see that we have a light blue line on the positive real axis, and it goes yellow, green, blue, dark blue, red, and then we go up to this picture, and we see yellow, green, blue, dark blue, red going clockwise. It's the other way around, so those are poles. So the directional content of the colors tells us something about what's happening with zeros and poles. And it's actually a beautiful technique. And I wouldn't know about it if it wasn't for Nick Trefethen's review of Uyghur's book in Siam Review. For those of you who are trying to figure out what these Maple commands are, I am apparently running a masterclass in Maple next month. But this stuff at the bottom, just pretend that's not there. That's a secret hack that allows people to blow things up programmatically. I don't have the manual dexterity to grab the corner and then make it come out in any reliable way. So I much prefer a programmatic command, and it's going to be much nicer in the next version, I'm told. Skip over pseudo pseudogammas? No, no pseudogammas. There's our sync function we've done there. There's lots and lots of, see, I told you there was lots of stuff. All right. I do want to tell you what Stirling's original formula was. If you ask Maple for the asymptotics of the log of the gamma function, it says, no problem. I know Stirling's formula. Stirling's formula in quotes, the one that everybody knows is Stirling's formula. And if you say instead asymptotics of gamma, it actually does a translation of that that looks really awful. It's got 1 over z to the z, the e to the z, and there's reasons for that because powers and branch cuts and closures are awful in the negative real axis. So unless you do it that way, you actually get the closures wrong. So Maple is trying to give you a formula that's valid, not just absent the negative real axis, but actually right up to one on the top. I don't know whether it succeeds or not, but it's trying. But this is in fact just the exponentiation of the previous one. And these numbers that show up in here are Bernoulli numbers. Sorry, these ones are the Bernoulli numbers. These ones tagged in the 80s and has an interesting connection with the other function I'm going to be talking about later. So I'm going to call that Stirling popular. And there's the formula with the Bernoulli numbers in it. So the log of gamma of z is asymptotic to this. Series is, of course, divergent, but nobody in the room is afraid of divergent series. And there's a better formula, frequently reinvented, twice as accurate, and nearly as simple. Some even call it simpler. Stirling's original formula has not z minus a half times log of z, but z minus a half times log of z minus a half, minus z minus a half. And then all the powers are in terms of z minus a half. So it's only trivially different from the one popularly known as Stirling's formula. We still have Bernoulli numbers in it, but now we've got an extra factor here. Why is this better? Instead of 1/12, we have 24. Where we had a plus sign before, we now have a minus sign. So it's twice as accurate, and the error is opposite sign. Oh, okay.
Trapezoid rule versus midpoint.
Yeah, that's wonderful. So the way I found this was exactly that. In the monthly articles, there are new proofs, improved proofs, notes, yet another new proof, and my favorite, the n plus first proof of Stirling's formula. And there are about 10 of them. There's about 26 in all on Stirling's formula. There's more than half of the 50 papers in the monthly are on Stirling's formula. It's very popular. And about 10 of them use trapezoidal rule. And I'm talking with John about this. I said, no, the midpoint. Why don't I try midpoint rule? So I derived using the midpoint rule in what I thought was a new formula. I went to John, I said, this is a new formula. It's a new formula for asymptotics of gamma. And John went, no, you can't say that. You might say that to the best of your knowledge it's new. But this stuff is being studied for nearly 300 years, and there's an awful lot of stuff out there. To say that you've got a definitively new formula for gamma, sure. He discovered that he was right. He died before we finished the paper, but he did learn that he was right, that it was new. I found a paper from Burnside 100 years ago that had this z minus a half in it. But Burnside didn't know Stirling's original formula either. He independently redid it. And there are several people who reinvented this thing. So, okay, me too. I reinvented it as well. I feel happy that I was able to reinvent something like that. But to go back and read the Tweddle's wonderful translation of Stirling's original work and the annotated, there's another gem to take home. So there's math history work by Tweddle, the collected works of Stirling. Go and really read how Stirling actually did this. It's lovely fun. And you see that it really is this Z minus a half formula, but Stirling didn't use a midpoint rule. He did it a completely different way of deriving the formula, and he had an algorithmic way of generating the next term. And he did not know that these numbers were Bernoulli numbers, or related to Bernoulli numbers. It was de Moivre who understood with his formula that they really were Bernoulli numbers. So de Moivre deserves some credit. What's really funny is that some of the other reinventors of this formula have taken to calling it the de Moivre formula, and not knowing that Stirling really invented it. But I think that's actually okay. We have actually Newton inventing symplectic Euler method, and Euler inventing Newton's method. So, why don't we swap between de Moivre and Stirling? I'm fine with that. So the key for us is if we ignore all of the 1 over z minus a half terms, we get an approximate half. So the very simple initial approximation. And in some sense, it's simpler than the de Moivre one, because now we have the same argument here, here, and here. And that's going to be important for us when we try to invert. I have a paper with my PhD student, Leili Raffier-Silvieri. Hello, Leili, I hope you're listening. On using Stirling's original formula and Levin's U-transform for sequence acceleration to simply as a method for evaluating the gamma function. It works quite well. I'm not going to talk about Levin's U-transform. That paper has appeared in Experimental Mathematics, so feel free. Skip, 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 skip. Skip the proof. Functional inverse of gamma. This image was done by my PhD student, Stephen Thornton. Stephen also did the image that's on my t-shirt. Those of you who are bored with special functions now and want to do eigenvalues, please go to bohemianmatrices.com and investigate the pictures of eigenvalues and matrices on there. There are some open conjectures you can work on while I'm talking and still look. You can still look alike, so that's really good. Anyways, Stephen has a freely accessible collection of MATLAB files for doing Newton's method, and he, at my request, did this one for the log of the gamma function. I didn't even know which value of x this was for, but the first time I gave anything like this talk was I was in Oaxaca at a Burrs-sponsored meeting, and it was basically the Day of the Dead, so it was really a very appropriate set of colors here. But there's one important thing you can see from this picture is this funny Y shape in here. And I think that we're going to wind up having the principal branch of the functional inverse matching that Y shape. But that's work in progress. We're not there yet. All right, well, in all of those papers in the monthly, there was not one that talked about the functional inverse of gamma. Nobody seemed to want to solve an equation, x equals gamma of y, and solve that for y. Seems very strange to have an omission since 1894, the 100-year history of the monthly, nobody talked about it. But we could find only 4 papers in the literature, anywhere, that talked about the functional inverse of gamma. The earliest of it was 2012. That's a very strange gap in the literature, so, well, let's try it. If you ask Maple to solve gamma of y equals x for y, it says, oh, I know. It's the root of this thing, which is correct. That's Maple's internal structure that says this is the solution of that equation, and you can do things with it. So, for example, you can plot this one. Well, this is new to Maple 2019. Maple 2018, you would actually crash. So I'm glad that I'm not running Maple 2018. But now it just gets unexpected branches. It jumps from one branch to another of the solutions. I don't like that. I don't like the way of plotting the inverse function that where you solve the equation and then plot the resulting solution. Luckily, we don't have to do that. It's
What is
not-
its representation? Do you know? What is Maple's internal representation?
There it is.
No, but I mean, it normally has some internal structure behind, doesn't it? So
Okay,
do
so
things with it. It might be, yeah.
the root of
Yeah.
thing itself is the data structure that means the solution of an equation. And it picks up a unique variable, in this case underscore z, that represents the thing to be solved for. And that structure is just a functional handle and an argument string is understood by a lot of routines in there. You can differentiate it, you can integrate it, you can plot it. When you ask to evaluate it, it will try Newton's method with various default guesses on it. So when you want to know what the internal structure is, I can actually point to it. I can't point to all of the things.
So
that
the
don't
other
run
routines
that.
which call it have to do the work.
They have to do the work.
Just deferred, basically.
This was invented before object-oriented became a thing. There is lots of object-oriented stuff in Maple, but this particular content, it was instrumental in a lot of things. So, all right, well, we've seen the graph of gamma before. We want to draw the graph of the inverse of gamma. You just swap x and y. I had x and gamma of y. It's gamma of y and x. Pardon me, gamma of y is x equals gamma of y, and then y, and then I plot that from y from minus 6 to 4. So you don't need to be able to evaluate the inverse function in order to plot it. Oh yeah, this is what we teach our students in calculus. Just interchange x and y. Well, we can do that. Surprisingly, this works for Riemann surfaces. So if I get to the Riemann surfaces, we will see this technique also works there. So there's the real valued inverse, functional inverse of the gamma function. And you can see that it's very definitely multivalued, as one would expect. So let's look at just the positive values. So here's the two branches that have positive values. So that's about 0.88 there, and about 1.46 in height. It's the branch point. So we have two positive branches. I'm going to say, I like that one. That one's going to be the one that's most useful. It's the one that it solves the inverse factorial problem. If you want to know, you've got 5,752, and you want to know what factorial makes that, that's the branch you want. Okay. Let's use Stirling's original formula. So I get rid of that sum with the Bernoulli things just by letting the inert function SUM, I just replace that with the function 0. 0 is a function in Maple. If you say 0 of something, it's the function which is 0, whatever that stuff is. So okay, the result is 0. So evaluate the original formula with sum equals 0, you just get this. Great. Solve that equals log x. Maple says no problem. Here's the solution. The solution is e to the Lambert w of 1/2 log of 1/2 x squared over pi divided by e plus 1, and that plus 1 is still in the exponent, and now we have plus 1/2 at the end. How many of you, this go back to the question, how many of you have written the book on the Lambert w function? Nobody. I'm trying to write one with David Jeffrey, but anyway. How many of you have written code? Well, I don't know. How many read a paper? Read a paper. There we go. We're down here. So we have read papers or heard lectures or something on that. Well, what is the Lambert W function? You can go to, these posters are arriving and being couriered over from Western Ontario. In the meantime, I managed to print one on a local thing, just a small size. You can pass them around. You can get your very own copy by going to this link, orca.on.ca/LambertW, and download the PDF and print it in your own printer if you like, or you can just wait till the end of the week and I can hand you one. You don't have to go to that poster to find out things about Lambert W. You can go to Wikipedia. And until last week, I had not touched this page. But I thought if I'm going to be talking about it, I will go and look at it and see what it says. And there was a smallish error in the first part, so I am now a Wikipedia editor and I've corrected that. So there we go. So what is Lambert W? Lambert W is the functional inverse of W e to the W. Oh, is that it? Yeah, that's all it is. But it turns out that this function was also invented by Euler in 1783. And he was working on using a series of Lamberts for solving a trinomial equation from 1758. So not that much older than the gamma function, which was 1729. But it is slightly newer. I promised an old special function and a slightly newer one. So slightly newer special function.
And Lambert from which year? So Lambert was after.
He did work in forget that. He did work in map making. The Lambert projection is still used. All kinds of stuff. He died at age 49. So if you're upwards of 49 and still producing, well, okay. Maybe this is Lambert here. When he met Frederick the Great said, "So, what kind of science do you do?" "All of them," said Lambert. "All right," says Frederick the Great. "What are you the best at?" "The same."
Was he Swiss or German?
And he was born in Mulhouse, which was then part of Switzerland. So I think he thought of himself as being Swiss. But things were different. So this poster, by the way, is the most unusual publication on my CV. It's under the category Other. Of course, it's not referee, but it was never done for a conference rating. This was funded by ETH, so Gaston Bonnet supplied some money from ETH, and by MapleSoft, and by Western Ontario, Ontario Research Centre, and we just made a bunch of them in 2004. We still have a lot left. We've been giving away thousands, made thousands of them. And people read it, they try to cite it. It's hard to cite a poster that's being given away. It's got this web address. The citation of this poster that I like the best is due to André Leclerc. André Leclerc has an asymptotic formula for the critical zeros of the Riemann zeta function, assuming the Riemann hypothesis is true. And he expresses these in terms of the Lambert W function, and you get very, very accurate Riemann zeros using the Lambert W function. So the Leclerc paper is cited in the paper with John. All right, well, this means that we have a formula for the functional, approximate formula for the functional inverse of gamma in terms of the Lambert W function, which Maple knows, and Mathematica knows, and MATLAB knows, and all these. So we can actually evaluate the functional inverse of gamma using this formula. We can simplify that formula a little bit. E to the W can always be replaced with W over something, or something over W. So you can simplify it to get, I'll just sit right down here, a formula that is 1/2 plus something over Lambert W of something. It's not very complicated. We'll go back and look at it. But I want to show you the agreement. The red line is using the principal branch of Lambert W. And this is an asymptotic formula that's valid only for large values of x, like 1. This is an astoundingly accurate asymptotic formula. We're out by 4% down at the bottom. If I switch to using the other branch of Lambert W, the other real branch of Lambert W, it actually curls around the corner. This is an asymptotic formula that's valid out there that gets this so correctly that it can turn the corner. And then it says, no, I'm sorry, I have to go complex. No, I can't go any farther. But I'm just really pleased with the accuracy of this formula. One of my colleagues said, well, yeah, Stirling's formula itself is famous for being really, really accurate. So the one popularly known as Stirling's formula is known for being really, really accurate. So if you make it better, well, of course it's going to be accurate. Nonetheless, I'm still very happy with that. Let's just look at that formula a little bit more. So if I want to use another branch, that's the branch index in Lambert W. If I don't have it, the branch is 0, it's the principal branch. So 1/2 plus the something over Lambert W of the same something divided by E. It's not a very complicated formula. If we use Stirling's own example, he used his formula to get gamma of 1,000. Well, that's 10,000, I changed it. So, all right, gamma of 10,000 plus a large imaginary component gives you, here's the built-in Maples gamma up to 30 digits of that ugly complex number. And if I ask for the residual, I want to take my formula, take gamma of it, and see what, subtract out what it's supposed to do. And we see that we have a residual of around 10 to the minus 5 on there. Well, here, what I'm applying my formula to is 10 to the 23,000. Okay, there, that's really, oh yeah. If we've got a gamma function goes much faster than exponential. So its inversion grows much more slowly than logarithm. So I gotta go miles out that way to get any kind of height up here. The same is more or less true in the complex plane. I will mention at this point this 2012 paper of Uchiyama in the Proceedings of AMS, which has a nice integral representation for the principal branch of inverse gamma. And H.L. Peterson has done some work on those. It turns out that I was not the first person to discover this formula in terms of Lambert W. Dan Lichtblau knew it, and David Cantrell took it from Dan Lichtblau, 2001, it's in there. I went back and looked at Gaston Gonet's original 1981 paper, and the reason he invented Lambert W was so that he could invert the factorial. So he did it in 1981. Thank you, Gaston. But nonetheless, this paper of mine and John's is the first place the proof has appeared. Now you get to vote. Do we want to talk about the complementary error function? Do we want to talk about the series for reciprocal gamma about the same, about its zeros? Do we want to talk about the branch point series, or do we want to talk about Riemann? How much time do we have left?
About 10 minutes.
Okay, so 10 minutes on a subject of your choice.
Riemann surfaces.
All right, here, Riemann surfaces loud and clear. And of course, I will share the worksheet so anybody can always look at the other stuff if they want. So this is work in progress. Anna Camargos Couto and David Jeffrey and I are working on this together. Anna is a graduate student of David Jeffrey's. Let's just hit a restart so clean up all of the stuff that's in there. Here is how to plot a Riemann surface. Actually, let's see if I already did that. It's a little bit slow. So I have a three-dimensional surface here. Why is that a portion of the Riemann surface for gamma function? Well, I've used the trick of inverting by putting u and v as the x and y. And then I'm plotting as the vertical height something called charisma. And I'm coloring this by the y, the actual height. I could color it by the charisma if I wanted. Why does that work? And the reason is, that this was in Cleve Muller's, in MATLAB, when he wanted to do complex plots, he actually put in Riemann surface plotting. And I looked at that, why does that work? He was plotting Riemann surfaces computationally. And the reason is that if I have those three things, the U and the V and the charisma, then I can reconstruct the X and Y and the U and V. So that corresponds to exactly 1 point on the map of X, Y to U and V. And of this four-dimensional object, by taking only three things, but just such that I can reconstruct that fourth one that's missing. Where there's an intersection, I can't do that. So I have to be a little bit careful, so I know that the solving process, if I've given U, V, and the charisma, by the way, the name charisma is due to David Jeffrey. You have to plot something, because you want to separate the sheets of Riemann surface. What separates the sheets of a Riemann surface? Well, some quality. Why not call it charisma? I like that. So the Riemann surfaces are slightly different.
Remind us again what this charisma is.
In fact, it's just a random linear combination of X and Y. I could have just chosen Y, which I often prefer, but you know, if you choose a random linear combination of X and Y, somehow that makes it generically more likely that you're going to be able to recover the other things. David and I wrote a paper in the 90s called Graphing Elementary Riemann Surfaces, where we discussed this technique in great detail. We didn't have the lovely name charisma, but we have nice Riemann surfaces for lots of things. And let me just go back to the poster.
Is there any way to recover branch points of the surface?
Yes, you have to identify them, of course. You have to figure out where the branch points are. But this is the Riemann surface for the Lambert W function, right here. And it's plotted in the same direction. And you can see that there's a self-intersection here. These ones down below come up and shoot through the red ones there. So along that little segment, we cannot solve uniquely for the missing component. Okay, but I colored it by the missing component. So you can see there's a different color there. So you can see that looks like an intersection, but in four-dimensional space, it's not really an intersection. So this is a very, very useful tool to be able to visualize complex functions. I'd like to say that it's foolproof, but it is not. And in particular for the gamma function, which has this enormous dynamic range. It's ridiculously small. When we saw the real graphs, just going over here, it gets flatter and flatter. Those are like n factorial. In between n and minus n plus 1, it's like 1 over n factorial. So that gets really, really small there. And of course, it's going like n factorial out here. Okay, so trying to choose a right scale and trying to choose the right box and trying to prevent your software from connecting different sheets from one to the other is kind of a pain. And choosing the right colors to make it look good, well, this is work in progress as we were doing now. So I welcome people to help me with work on the Riemann surfaces. Riemann surface for gamma 1 over z is strongly related, so we can wind up doing things like that. But I think I'm actually just going to stop there, and I'll just say that this work is supported by NSERC and by the University of Western Ontario, and in part by ETH, and by the goodwill of everybody who sits and listens quietly. Thank you very much.
Questions?
That must I think elementary question. So at some point, maybe 5 years ago, I published some paper, and an intermediate step, I had to use some generalization of Lambert W function. Basically, instead of x e to the x, it's x replaced by some series, you truncate, and then I had to invert. And when I found playing with inversion, you can really speed up with asymptotic formula, you know, not even others. Like,
Wonderful, a fellow member of the.
is that something known?
No. No, generically, solving nonlinear equations, exponential polynomials, the mixture of polynomials and exponentials, is extremely difficult in practice. There are isolated examples where you can do it, and generically, there's no known way to do it except asymptotics. The delay differential equations community knows the most about bounds. These things come up in solving delay differential equations, and so they've worked out very good ways to get approximate solutions in lots of situations there. But when you have, that's with multiple delays, but if you have higher degree polynomials in front, that's not so interesting for them, so they don't have results there. But it's fun, and I'd like to see your paper.
It was also fun to do this. It was intermediate step, but very helpful later.
That lambda function W. Would you comment, what was the idea of derivations, I think?
So this is a very, very standard derivation, in fact. So this integral formula here,
Yeah.
you're looking at. So if you do this, actually, can I do it?
There's also Euler formula.
No, I need to erase. I'm erasing things. Now, if I can remember what the integral is, it's the usual.
Where's the poster sheet?
And the contour, I remember that. So, of course, yeah, you can read the front of the sheet. Well, no, I know what the real integral is, right? It's the derivation that I'm trying to get. So, in fact, all I want to use is Cauchy integral formula in here, so I guess I want exactly pardon me, yeah, that's right. Just a standard Cauchy integral formula. So now you prove that as the radius from 0 goes to infinity, that W is, which is like logarithm, so you have like logarithm zeta over zeta squared, that goes to 0 quickly enough so that you can say that the contribution on this part goes to 0, and you're left with the contribution coming in under here, going around and going back. So you wind up with essentially a real integral, and then you do a change of variables. You do the change of variables that's suggested by the contours of so this is written down in my paper with Peter Borwin and German Kabugen and David Jeffrey. It's papers in the Integral Transforms and Special Functions 2010 or something like that. But it's pretty straightforward, and German took it a lot farther. He gave lots and lots of different integrals for Lambert W and related functions. But this particular derivation is actually very standard.
What about the integral representation of the inverse lemma?
It involves a Borel measure, and I don't actually understand. I'll give you the paper, and you can explain it to me later. This is the, where is it? I have a copy of the paper. It's only 6 pages long. So, yes, the integral is equation 2.1 there. Let me know what you think of it. I know this integral exists,
But while Scott solves that particular problem, are there any other questions?
Have you come across the relation between the gamma function and Runge's phenomenon in numerical analysis? There's a very simple
there is an interesting
involving
question.
that and sine, infinite product of sine. Anyway, I use that application. I just wondered how well known it was. I'm not
The answer is no, I haven't, although I've just recently published a paper with Layli, the same person, on the Runga phenomena in SIAM Review in the education section.
I'll be very pleased to read that, see if it relates to what I've done.
But I don't think it has the slightest thing to do with the gamma function, but.
But did you get a formula for a simple formula
No.
for the magnitude of Runga's phenomenon?
No, we weren't looking for that.
You can write down the explicit formula for the error,
Well, yes, you can, yes.
just counterintuition.
I'll explain how.
Okay.
If there were no Runga's phenomenon, if you were thinking of interpolation on equally spaced points, which is a terrible thing to do, if in some different universe it worked regularly, it would be like a sine function, wouldn't it? Well, the ratio between the sine function and what you actually get with Runga's phenomenon is a simple explicit expression in three gamma functions.
Very cool. So going backwards, we would have the inverse gamma function, or lambda W.
Yes, yeah.
I love it.
So gamma's got an infinite number of Stokes lines for this ring.
Yes, it's a mess.
So you've seen Bill Boyd's stuff, yeah.
So I have not. David Jeffrey, I believe, has. But what
It's in Proctor sockets, he does it in detail.
okay, I would like to see that.
And there are probably also integral representation when Z is not real, right?
Yes. Alexander Kafitz came up with a number of other integral
For all
representations.
branches.
Yes, yes.
There is also this kind of classical, maybe also Lagrange or Euler formula for integral formula for any inverse function. You want to
Yes.
you want to find say W equals f of z,
Yes.
and you write integral when in the denominator you have
It's
W
quite related to this
W
function.
minus f. This is what you eventually have in your formula.
Yes. You have the difference in the branch on the top and on the bottom there is really what's coming up, yes.
Scott, are you ready?
I'm going to film my lecture, so.
I look forward to it, Scott. Yeah.
If Scott isn't able to solve that, then we'll thank the speaker again.
Thank you all.